All right. This presentation is an overview of the topic of stress transformation with combined loading. This is a structural mechanics topic which builds on a firm knowledge of stress states and coordinate transformation. It's a lot of topics combined into one here. All right. We'll start by briefly reviewing the topic of coordinate transformation. Coordinate transformation is basically just rotating the current or original axis using the transformation matrix beta, which is a 3x3 matrix for 3D case. It is derived by taking the dot products and the dot products of new and old axes vectors, but we won't go into the math here today. But essentially the beta matrix becomes simply a combination of the cosines of the angles between each axis. Beta has the special property of being orthogonal, which means that beta transpose dotted with beta original equals 1. This coordinate transformation can be done in one step for a simplified 2 case or multiple steps for a 3D case, which consists of rotation about more than one axis. So you have your original axis and you want to change that to a different reference of this axis here. And so all of your coordinates for your original, if you take that and multiply that by your beta matrix, you get your new axes. Now, there are multiple reasons we might want to use a coordinate transformation. The first is for convenience. The original coordinates that you are given might not work well with the geometry of the objects you're dealing with. For example, car companies will have a global coordinate system for the entire vehicle, where the x direction is front to back, y is left to right, z is up and down, and the origin is at some point on the vehicle, such as the front center of the car or the center of gravity. All the parts of the car will have to be made to fit this global coordinate system, but designing specific parts to this coordinate system would be less than ideal, depending on the orientation of the parts, because that might not be the most convenient to use. So we use, or CAD uses, coordinate transformation to transform this global coordinate system to a more convenient coordinate for design. But because they're it's been transformed, it still works with your global coordinate system. You just use it as a reference, and you can switch back. In addition, we might want to study a specific orientation. For example, if we have two pieces of wood that have been cut at 45-degree angles and glued together here, this surface might be your weakest surface, so you're kind of concerned about the stresses on this surface. So you want to rotate your coordinate system from the original x, y to this new coordinate system along the surface, so you can get a feel for what the stresses are on this surface. This ultimately leads to stress transformation, which is using your coordinate transformation to transform the stresses as well. Any stress state we are given is with respect to a certain orientation. So if you're viewing an object according to this coordinate system, it'll be different than if you rotate it, even though it's the same object under the same stresses. You can transform the stress to any new orientation using this equation here. And this is the same beta we've used for coordinate transformation. And remember how I said that beta is orthogonal, and so beta dotted with beta transpose is 1. So that's kind of a useful property here. So we maintain all of the original vectors, dots. As we rotate, these stresses will change. That's basically what we're trying to say here. So let's go on to the next one. The principal stress transformation is a specific type of transformation. Now we know that the stress state changes as we rotate the coordinate system. This normal stress might increase, this one might decrease, and these shear stresses will decrease or increase. They're all the same stress from the complementary property of shear. At some point along this rotation, these shear stresses will become 0. And so you're left with purely normal stresses. And this stress state is your principal stress state. So these are your principal stresses. They usually have a 1 for the largest, and 2 and 3. 3 would be your smallest. And in this case, your third is 0. And these principal stresses occur at the principal direction, which is an angle from your original axes to one of the normal surfaces of your new orientation. You can calculate the maximum normal stress that a body can have at a single point, which is simply the maximum principal stress. And similarly, the maximum shear can be calculated from the principal stress. The maximum shear stress is half the difference between the maximum and minimum principal stresses. And it can be found along a direction that is 45 degrees from the principal direction. These principal stresses are quite useful for failure analysis. For example, the von Mises failure theory says that when the von Mises stress surpasses a material's yield stress, the material will fail. And this stress is calculated directly from the principal stress. Other failure criteria include the Tresca failure theory, which is related to principal stress through the maximum shear stress. This is a simple diagram of your boundary for failure due to von Mises, which is the outer oval, and this other shape, which is the maximum shear. As you can see, it depends on your principal stresses. And this one specifically assumes that your third principal stress is 0, like in the example on the past slide. Looking in a specific orientation, you might not think that a material will fail if the stresses in that stress state are well below the yield stress, but changing the direction might reveal higher stresses that do, in fact, surpass the failure criteria. The last piece of the puzzle here is combined loading. Any object might be subjected to several different loads, which all inflict different stresses on the object. The combined loading concept combines all of these loadings into a single stress state, which consists of the normal and shear stresses combined for the different loads. All these different loadings will simply boil down to these stresses. You got normal stress and shear stress. Normal stresses from bending and from a normal stress, and your shear stresses from a shear force or from a torque. And all of them kind of combine to this new stress, not a new stress state, but it combines all of them. Now we are going to work through an example of principal stress transformation with combined loading. This cantilever beam has 3 torques and a normal force applied to it. And we want to find the principal stresses at point H here. This problem will require knowledge of combined loading, stress state, and principal stress transformation. The first step would be usually to calculate the reaction forces. But in this case, we do not need to do that because we already know all of the forces on one side of our cut. So the first step will be to find the internal loadings at a cut through point H. So you will find that these 3 torques combine to form a single torque of 55 Newton meters, and the normal stress remains the same. Be careful to carefully consider each direction, because those torques were in different directions, and you want to make sure you have the right directions, because otherwise you'll have errors in the future. So these are your internal forces at the cross-section through point H. Now we want to find the stresses caused by the internal loadings at point H. The stresses will vary across any point on that cross-section, so we want to be careful to consider the stresses that occur specifically at this point H. I mean, if you choose any other point here, they're going to be different. From torsion, you'll find that your torque is your 55, and your R is the distance from that center of where the forces are acting to the point in question, which in this case is just the radius, which is half of the diameter. And your polar moment of inertia is simply this equation here, where this is your diameter. Your normal force is simply your normal stress is simply your normal force divided by your area. And so from these 2 calculations, we have a shear stress and a normal stress. We do not have, in this case, a stress in the y direction. Now we can find the stress state at point H, and the hard part here is knowing what's negative and what's not. So the stress state is, along the diagonal is your normal stresses, X and Y, and both of these are going to be the same because it's a symmetric matrix, and this is your shear stress. Now this stress is compressive. It's actually the same across the whole cross-section, and so because it's compressive, we know it's negative. And the shear is a little more complicated. Torsion will cause a different direction based on what point you are. And in this case, at this point here, if you imagine this arrow going all the way around, at this normal surface, it will be pointed directly up. And because this is the positive surface and it is going in the positive y direction, it will be a positive shear stress. If it was on the other side, it would be negative. We can use this stress state to calculate the principal stresses, principal directions, and maximum shear stress. This is the equation for principal stress in 2D. And in this case, your normal y direction will be 0. Simply comes out to 1.7 megapascals and negative 11.3 megapascals. And your principal directions, there's a few different equations, but I find this one's the most useful because you can directly relate a specific principal direction to its corresponding principal stress. So the principal stress of 1.7 megapascals occurs at 68.7 degrees from your original x-axis. And your maximum shear stress can be calculated from the maximum and minimum principal stresses. So the difference divided by 2. Finally, we will draw the principal stress state. And given the principal stresses we found in the last slide, we find that this angle here, which is actually from the normal surface, is 68.7 degrees. And as you can see, there are no shear stresses on here, which is what makes it the principal stress state. And that is the example for principal stress transformation with combined loading. Thank you.